Thank you for the introduction, Michelle. My name is Michael. For the past 2 summers, I've been doing research with Professor Robert Karpik in the mechanical engineering department. So I'm going to be talking today a little bit about a field called mechanochemistry, which has a lot of promise for making the way we do chemistry more sustainable and energy efficient. And then I'm going to be talking about my research and how it fits into that. So when we think about chemistry, we usually think about something like this, a bottle with some liquid in it. That's because the majority of chemistry that's done today is what's called solvent chemistry. You have the materials that you want to react together, you dissolve them in a liquid called a solvent, and then usually you use heat to make the reaction happen. Now, this has some problems. Chemistry right now is a big producer of waste, and a lot of that waste comes as a result of solvents. So on average, industrial chemistry produces 20 tons of solvent waste for every 1 ton of chemical product. And that's because you need large quantities of these liquids in order to dissolve your reactants. And then also, usually afterwards, you have some complicated procedures to sort out your products, a lot of stuff like that. So what is mechanochemistry and how does it help address this? Mechanochemistry is a fundamental change for how you would do chemistry. So mechanochemistry uses physical forces instead of heat to catalyze reactions. What this means is that you don't need a solvent. You don't need the liquid in the equation at all. And so that greatly reduces the amount of waste that you have because you don't need the solvent at all. And mechanochemistry also has several other important benefits. So one is that in most cases, it's more energy efficient because in solvent chemistry, while you have to heat up your entire system, you have to heat up the entire liquid, you're using more energy than you need to just overcome the activation barrier. Here in mechanochemistry, you can target more the energy you just need for the reaction. So a lot of these reactions are more energy efficient. In addition, a lot of work has shown that mechanochemical reactions have greater yields than traditional chemistry, which means that for the same quantities of reactants going in, and the same energy going in, you have more products coming out. Other papers have shown other really interesting stuff, like you have more chemical selectivity, meaning that you have fewer unwanted byproducts. Nobody really knows why, but it's a thing and we like it. So why aren't we using mechanochemistry for everything? Well, that picture up there is what's called a ball mill reactor, and that's kind of the standard in mechanochemistry right now. How it works is basically you have this large spinning drum with a bunch of metal balls inside. You put your reactants in powder form into it and you spin it around and all the balls are crashing into one another and you have all these, chaotic collisions. Right now, there are no models that accurately predict how the forces inside of this behave. So we don't have any ways of understanding really what's going on. So we get reactions for some things, but we don't know why. So it's hard to expand this process to use it for other reactions. In addition, it's not very efficient for energy use. As you can imagine, you're having all these crazy collisions. You're not being, if you just targeted your physical forces for breaking or forming the specific bonds, you would be much more energy efficient. And so that's where my research comes in. So in my research, instead of using these large macroscopic systems, we were looking on the nanoscale. So recently, there have been a lot of advancements in nanotechnology, which allow us to really study these systems on a very small scale. So what this image is here is called an atomic force microscope, which is basically a cantilever with a needle at the end of it. The needle has a radius, usually in the nanometers, can be as small as like 8 nanometers up to maybe 50, or you can go even really big if you want. But the point is that with this machine, you can very specifically target small areas for very controlled experiments. Not only do you have great control over where your experiment is and which molecules or groups of molecules you're targeting, but you also have very good control of the forces involved. So you have very, very good load control. And as opposed to the ball mill reactor, where you don't know if the forces involved are shear forces or collision forces, compression, or whatnot, here we have very good control. We know what's load, we know what's friction, And as we're running our experiments, as we're trying to catalyze our reactions using this, the atomic force microscope is great because it also functions as a microscope, which means that while we're doing this, we have sub-nanometer resolution of our reaction as it progresses. So this blue image here is an image I took over the summer with an atomic force microscope. And I just put it here to show the very fine control and very fine resolution you get with these things. So in the image, you can see, details up to a couple nanometers. And in the Z direction, you get sub-nanometer resolution, which means you know what's happening up to like single layers of atoms, which is very exciting. So what are we using this for? We're using this for a relatively simple chemical process. It's an organic chemical reaction. For any chemists in the room, it's a Diels-Alder reaction. For everyone else, all you need to know is it's a one-step reaction that's used for, it's usually one small step in a lot of organic chemical processes. It's used in a lot of pharmaceuticals. And classically, in solvent-based chemistry, it's very well understood how it functions. So it's a very useful thing to look at with mechanochemistry. It's a good, because we know how it should work. So now we see how it works differently in mechanochemistry. So what are the results that we had? We were able to successfully have a reaction. And not only that, but using the atomic force microscope, we're able to watch the reaction as it progresses. So this is a big change from a ball mill reactor where you throw your stuff in, you have it happen. It's a black box. You have no idea really what's going on. And then you either get a product at the end or you don't. Here we can watch it happening. This is a little image of the product that we got at the end. So that was big that we successfully were able to synthesize a chemical, and we were able to do it using forces, which is kind of exciting. And not only that, building off of this, the group has done further work doing multiple experiments to show that we can also have control over the reaction rate based on the stresses that we're applying. So more force, we can have faster reaction rates. So why is this important? Essentially, the big takeaway from this is that a lot of work right now is being done on making chemistry more sustainable, more energy efficient. Mechanochemistry is a fundamental shift in how we would do chemistry. Instead of working on the pre-existing systems, we're trying to do something entirely new that has the potential to be much more sustainable and much more energy efficient. And this work shows that we are starting to develop that understanding of what's happening at the nanoscale that allows these physical forces to catalyze chemical reactions. So it's very exciting. Happy to take any questions.